Hello everybody. I welcome all of you to the last presentation of this session, which focuses on all the research that we are doing under the banner of facets. So title of my talk is Designing Watersheds for Integrated Development, Combining Hydrological and Economic Modeling for Optimizing Land Use Change to Meet Water Quality Regulations. I am the speaker today. My name is Puneet Dwivedi. I am a faculty member at the Warnell School of Forestry and Natural Resources, University of Georgia. My co-authors on this paper are Ranjit Bawa, Nahal, and Dr. Latif Kaleem. Ranjit is a PhD student under my advisement. Nahal is a postdoc working with Dr. Brand Bledsoe at College of Engineering, University of Georgia. And Dr. Latif Kaleem is a full professor at the School of Forestry, Auburn University. And before I go further and start giving you more details about our talk, I just want to thank the organizers of Georgia Water Resources Conference for giving us an opportunity to come here and talk about our research. So moving on, this is the latest report that came out of Georgia Department of Natural Resources, Environmental Protection Division, and it's a very comprehensive report because they tell you exactly what is happening when it comes to water quality in the state of Georgia. So as you can see here on your left hand side, things are not good. For example, if you just look into streams and rivers, about 60% of streams and rivers in terms of miles, they are not meeting one or another form of water quality standard. If you look into lakes and reservoirs in terms of acres, you will find out that up to 40% of total lakes and reservoirs acres that we have in Georgia, they do not meet one or other form of water quality standard. So things are not good, and definitely something needs to be done. Now, why things are not good? So as you can see, most of the problem when it comes to water quality in the state of Georgia comes from non-point sources. For example, in the figure, the top left figure that you can see on the screen, you can see non-point source is almost 95% of all the water quality problems that we have when it comes to rivers and stream in Georgia, right? So definitely something needs to be done for sure. But as you know, regulation is not very popular because everybody assumes that whenever there is a regulation, definitely your economic well-off will start falling down. So then we started thinking about that, okay, let's test these normal assumptions that we have in our mind and in our state, in our society, and actually figure it out that what happens when you start tightening water quality constraints, then how your economic well-off start going down, and also what's the rate at which that economic well-off starts going down. So then we thought that, okay, our goal will be to assess the trade-offs between economic welfare and potential water quality regulations in the presence of land use changes at the watershed level. And then why we came out with this overall goal, because we know that as you are tightening your water quality regulations, your land use has to change, right? And if that is going to happen, definitely that impacts economic welfare. So that is why we thought that, okay, that makes sense, because that we can definitely relate it without any problem. Regulations lead to land use changes or changes in agriculture or silviculture practices, and those changes will ultimately result in economic changes in economic welfare. But we don't know how things look like in reality. So that is why we thought, let us do this morning exercise and try to figure it out. What is a relationship when it comes to trade-offs between economic welfare and potential water quality regulations, punctuated by projected changes in land use changes over space and time. So that was nice. So then once we decided to do something on these lines, we have to get hold of a watershed. So then we got hold of Little River Experimental Watershed, which, as you can see on the figure on your right hand side, is spread across 3 counties in South Georgia: Tift, Turner, and Worth counties. And it covers almost 83,000 acres of land. And the good part of this basin is, or watershed is, as you can see from the figure on your right, that it has a mixed land use. For example, about 50% land is under agriculture, 16% land is evergreen forest, basically pine plantations, 2% land is under hardwoods, and 1% land is under hay. But as you can also see, it has a big land mass which is under woody wetlands, almost 22%, and then we have stream networks and urban space which occupy close to 6% of the area. Okay, so and this is the spatial distribution of all the land uses that I just talked about. And then we realized that there is a really good data of water quality, water flows when it comes to this watershed, because our friends, our colleagues in USDA Agriculture Research Services, they are doing quite a bit of watershed related research from last couple of decades on this particular experimental watershed. So that is why we thought to work with them to figure it out how trade-offs between economics and regulations will look like when you are tightening your water quality regulations. So that is why we went back to our friends, especially Dr. David Bosch and few other folks, to get hold of this data, water quality data and water flow data, and they were really kind to help us out with that data that they have collected over so many years. And then we basically got all the data that we needed to develop this model starting from 1997 to 2005. So as you know, we have to have scenarios in order to figure it out, basically how the trade-offs will look like. So we created several scenarios for this study, but we can broadly categorize our scenarios into three categories. In the first scenario, we are just manipulating nitrate loadings at the outlet of the watershed. In the second scenario, we are just manipulating phosphorus at the outlet of the watershed. And in the last scenario, we are manipulating both nitrate and phosphate limits at the outlet of the watershed. Now, as you can see here, we start in under N1, which is scenario 1, just nitrogen or nitrate. So that is N1. We are putting a limit or regulation that each year of simulation, 48% decline has to happen when it comes to nitrate loadings. So 48% this year, and then so on and so forth. Each year 48% decline relative to the previous year. So for example, in N7, you are making sure that your nitrate loadings each year are going down by 72% relative to the previous year. So same goes for P and same goes for NO3 and P. Now you will say, okay, why you are starting at 48%, right? You can start at 30%, 20%, why not? So we did that actually. And I just want to tell you that we don't see any impact of changes in nitrate loadings when you are 20 or 30% in terms of overall land use, and as a result of which on the economic welfare, we only start seeing that land use has started changing when we go up to the point of 48% reduction each year in nitrate loading. So same is true with P. As you can see, we don't see any changes if you are reducing your phosphorus regulations by 1 or 2% each year. You only start seeing changes in land use changes, and as a result of which economic welfare when you are reducing your phosphorus regulations or phosphorus loadings by 14.75% each year, right? And then by the next question comes, okay, why you are not going more than 72%? And the reason is very simple, because if you go more than 72%, for example, in case of nitrate loadings, we see that basically model is not solved. So basically, which means that no matter what you do, you will not have an optimum land use, which can give you a reduction of 72% nitrate loadings each year for next 7 years. So that is why for this particular presentation, we are focusing on 48 to 72% reduction in loadings for nitrate, between 14.75% to 17.5% for phosphate. And if you start combining these two things together, the ranges differ, because as you know, now the model has to solve for both these constraints. Now moving on to the next slide, and this is the broad modeling approach that we took, for solving this problem or answering our own question. So first we used a very popular hydrological modeling or watershed modeling software, which is SWAT. We calibrated the model, we validated our results so as to make sure that our hydrological modeling is airtight. Once we had a calibrated and validated SWOT model, we figured it out that what are the nutrient loadings for each crop type for each sub-basin present in the watershed. These crop types included all the major crops that we grow in the watershed, plus also pine plantations and hardwoods. Then we also, using SWOT, we've also figured it out what are the crop yields, because that information is needed to figure it out how much money you are making over a number of years depending upon how prices are behaving over time. Then if you see here, we use the first two core parameters, nutrient loadings, and basically to figure it out that how much load is on an average each crop from each sub-basin is contributing at the outlet of the watershed, right? And finally, we took all these three pieces of information and developed a linear optimization solver, dynamic linear optimization model to figure it out that how, if you're trying to maximize economic welfare with respect to water quality constraints, then how your land use is going to evolve so as to maximize money or economic welfare at the watershed level over space and time. So this is our SWOT modeling, and I want to really give a big shout out to Nahal and Latif for helping us out on SWOT modeling, because we don't have any idea, me and Rajit, that how SWOT modeling works and what we should be careful about and how to actually do it. So their help is really appreciated, because this is the key piece of information, otherwise our model would have not worked. So as you can see, they did quite a bit of work, especially Nahal, on these lines to figure it out. Basically, what are the exact nutrient loadings, exact flows from a particular covered type for a given sub-basin. And I have been informed that results look really good, so I believe totally there is no question mark there, right? And then as you can see from this table, as per Nahal and Latif and all the other literature that talks about whether or not your calibration and validation is making sense, you can see these numbers and you can definitely know that our calibration and validation is really good in shape, because our KJE, which is an indicator that how good or bad your calibration and validation is, as you can see, most of these numbers are very close to zero. So the close to zero you are, better you are, at least to best of my understanding. So once I saw all these results and got in touch with Nahal and Latif and also some other big watershed modelers at University of Florida and other places, they were reasonably happy after looking all these things that we just did in terms of SWOT modeling. So then it was easy after that, because after that we knew how to move forward. So Dr. Latif Kaleem did a paper sometime back in 2009 to figure it out that how to ascertain relative contribution of sub-basin towards overall nutrient loading at the outlet of a watershed. And basically we followed the same approach to figure it out how much each sub-basin is contributing towards overall nutrient loadings at the outlet of the watershed. And the concept is very simple, because basically you create a fake rain gauge for each sub-basin that you have in your model. For example, we had 198 sub-basins, and put zero rainfall for that sub-basin for that fake rain gauge, and then you rerun the model in R to figure it out basically what is the relative contribution of that sub-basin to the overall nutrient loading. And then if you do addition and subtraction, then you can be very precise in your estimate. So that is the approach that we took, and thank God we had Dr. Latif Kaleem to help us out to figure out all these technical details. So thank you again for that. So moving on, then after that we came in to figure it out basically how to develop this dynamic linear problem where we are trying to maximize economic welfare over space and time subject to land use constraint. For example, we also took care of what happens if one land form moves to some other land form, because as you know, if you want to convert forest into agriculture, you have to pay $1,200 per acre so as to clear the land and prepare the soil for planting. especially agriculture crops. So we also accounted for all those costs or opportunity costs, if you want to be very exact, in our model for this particular research. And as always, we have to have a constraint on water quality. So that is how we were able to successfully incorporate water quality constraint in our modeling effort. So now coming on to the results, the most exciting part of any talk. So these are the relative contribution of each subbasin for a given year at the outlet of the watershed. So as you can see here, the outlet is somewhere here. As the pollutants are moving from this subbasin, which is sitting at the top, to the outlet, you can see that relative contribution of these subbasins which are sitting on the top of the watershed is much lower than the relative contribution of nitrate loadings from all these subbasins which are next to the water outlet, and which makes exact sense because these subbasins are all the nitrate which is coming from all these subbasins has much more time to travel downstream, as a result of which it decays. But all the nitrate which is coming from all these subbasins which are next to the water outlet, they did not have much time to decay, as a result of which relative contribution of these subbasins is much higher than relative contribution of these subbasins. Same story for each year. Things change here and there depending upon how much rainfall is happening and so on and so forth. But as you can see, there's a lot of spatial variability when it comes to nitrate loadings and relative contribution of each subbasin towards the overall nitrate loading at the outlet of the watershed. Right, so same story with phosphorus, nothing special going on, more or less same story that I just told you. As you are moving from top to bottom, relative contribution from each subbasin starts going up. This is surface runoff. As you can see, a lot of spatial variability, not only in a given year but also across years, and subbasins are contributing more towards surface runoff versus subbasins which are contributing very little. These are the results for economic modeling. As you can see, how much money you are going to make from each type of crop that we considered in our analysis depends upon what's the yield, which again depends upon climate and rainfall and management practices and so on and so forth, but also it depends upon the prices for that particular year. So we incorporated all that dynamics to figure it out how much money you are going to make depending upon what you are doing in your watershed and over space and time. As you can see, these numbers starts going down because we are using discounted values so as to get everything in net present value for at the start of the modeling period. Now this is how land use look like if you are just looking into nitrate loadings. So as you can see, this is the base case where practically there is no problems when it comes to pollution. You can pollute as much as possible. So that is the case we definitely want to avoid. Then you start tightening your constraints in terms of water quality, nitrate constraints, and as you can see, higher the constraints, for example N7 is 72%, you see more and more softwood is coming in, right? It once comes to phosphorus, that higher the limit is, more and more hardwoods are coming in. And when you are tightening both nitrate and phosphorus, as you can see, more hardwood comes in, but also a little bit of softwood also comes in. And as you can see, this model is pretty flexible in giving you exact spatial information over space and time. So all these figures that you see, they are the last year of the simulation, but behind all these number maps, there are 6 or 7 other maps for each year of simulation. Right, this is how land use change looks like if you just want to see magnitude, if you're not interested in spatial information. So that is how it looks like, right? As you can see, you started with Bermuda, corn, softwood and hardwoods, but as you are tightening your regulations, nitrate loadings on N7, you see basically at the end of the simulation period, you have only 2 major land use types. First one is softwood, second one is cotton, because then you are meeting your water quality constraints, but also you are maximizing your economic welfare. Right, same story with P7, you have more hardwoods at the end of the day rather than softwoods. Now the most exciting part, the trade-off analysis, as you can see here, as you are increasing your regulations, the economic welfare starts going down substantially. So if there were no regulations, the base case, you were making at the watershed level close to 195 million bucks. But as you are tightening your regulations with respect to N1, N2, and so on and so forth, by the time you really tighten your constraints, then your profitability, your economic welfare go down substantially, close to 40 or 45 million dollars, right? If you see here what is happening, if you start tightening your phosphorus constraints, your economic welfare also starts to going down. You were making same $195 million, but highest limit of P, right, almost 17%, then you are only going to make $160 million or so. So yeah, things change depending upon what the regulation is, but as you can see, definitely higher the regulation, less is the overall economic welfare. So which basically speaks to what we all know, that yeah, environmental regulations definitely will impact land use change, and those land use changes will in turn determine the overall profitability. And as you can see, higher the environmental constraints, lower is the overall economic welfare at the watershed level. Now this is the third scenario where you are tightening your P limit and N limit at the same time, and as you can see, it also has a substantial impact on economic welfare. Now, so major findings. Forestry will be key in meeting water quality standards in Georgia in general, or in Little River Experimental Watershed in particular. Spatial prioritization is a key. We don't have to plant trees in every nook and corner of a watershed so as to meet water quality constraints. Using these approaches that we have developed as a part of this research, we can spatially prioritize that where we should plant trees, where we should do agriculture, so as to meet water quality regulations while maximizing economic welfare. And definitely a DWID model that we have developed as a part of this research is well off in terms of optimizing for trade-offs between potential water quality regulations and economic welfare at the watershed level. Now, future directions, definitely now we have much more confidence in what we have done, and our results make sense, at least to us. Paper is in review, who knows what reviewers are going to say, but so far we are very happy with what we have done in a very short amount of time. But the idea is to test this model again in Flint River Basin and Suwannee River Basin, which are basically bigger watersheds, part of FASER's project. And not only that, we're also going to extend the existing status of DWID model with the stochastic modeling, and also we will try to bring agriculture best management practices so as to see how they will play out in economic welfare and water quality regulations in these two watersheds, especially Flint and Suwannee. Then definitely we are going to talk to policy folks to help them out to make good decisions where we are maximizing economic welfare while meeting water quality regulations. And definitely right now there is a big push on modeling for markets for ecosystem services, and these folks also need some information on these lines. So I am looking forward to work with them in the future so as to answer their questions for establishing markets for ecosystem services in Georgia or in South. And finally, thank you for your time, and I'm looking forward to be in touch with you. If you have any more questions, clarifications are needed, or you want to get in touch with me, please let me know on this email. I will love to talk to you. You can also follow me on Twitter. And definitely, again, before I close, I want to definitely give a big shout out to all my co-authors for coming together on this exciting project and developing something which anybody can do in their labs without much technical knowledge when it comes to advanced modeling techniques. So with this, thank you so much, and I appreciate your time.